All right, let's do it. So we're going to do another lecture on sort of robust and stochastic control. Last time, I mean, this is the tip of the iceberg of a big topic, right? I want to make sure I say that over and over again. It sounds silly to say I'm going to cover all of robust control in a lecture or two, okay? But I think I can give you some of the core ideas. And last time we talked about the more stochastic side of things, okay? So last time, so the picture I still want you to have in your head is something like the, we've got rich nonlinear dynamics and the rich propagation of distributions through the system, right? I want you to have that picture in your head when we're talking about these things, right? And last time we talked about sort of two cases where we could really solve everything about the stochastic dynamics and control. One of those was sort of the tabular case, the finite MDP. And the other was the linear dynamics plus Gaussian noise. And we showed that LQR, we could figure out LQR in that setting. And then we kind of had the full nonlinear case. So roughly what I tried to convey last time is that if your system is, well, if it's tabular, or low enough dimensionality, then you can basically do value iteration, right? You can discretize the space. You can treat these distributions as discrete distributions on a graph, and we can bring all that power into the system as long as the state dimensionality is low enough. In the other setting, if it's linear, then you can make a Gaussian approximation of, or you can use a Gaussian to cover this, and Gaussians propagate through a linear system, right? Or if it's arbitrary nonlinear, then you can just do this, what I'm doing for the animation. You can make particles, and you can send those particles through as your representation, right? And we could do nonlinear trajectory optimization directly on that. There's a few other things in the wheelhouse there. You can track higher order moments. Actually, polynomial optimization, sums of squares kind of methods would allow you to track, higher order moments of your distribution, not just the first moment, which would be a Gaussian. You could take a first, second, third moment of the distribution, have something that propagates through polynomial dynamics. There's actually some nice results in the middle there. But roughly speaking, this is all trying to do a lot of work to sort of track the details of the distribution. And if you have a representation of the distribution and how the distribution evolves, then the goal for control should be to somehow shape some statistic on that distribution. And we did like the average. The expected value of that distribution is a natural thing. You can write chance constraints. You can write other things against that. Okay? But last time we were roughly trying to think specifically about that distribution as a histogram, right? And how does it evolve? This time we're going to do something different. Okay? We're going to look more at the robust control, worst case analysis view of the world. And so think about instead, I'm going to ignore the details of this, and I'm going to try to summarize this with, let's say, a box or some other summary that says that I know that I don't know exactly what the distribution is, but I know it stays inside some finite box, okay, or a polytope or other shapes that we'll think about, and we'll show you the ones that are natural for computation, okay? And I'm going to just think about how that box evolves under the different dynamics, okay? And then try to make statements instead of saying, I can't now, since I don't even know the distribution inside the box, I'm going to make different statements. I'm going to say the box never hits a tree or falls out of the sky, right? Or the worst case, if an adversary is allowed to pick any element from the box, the worst cost I could possibly obtain is this, right? So it's all about worst case analysis. And it's nice in the sense, it's simpler in the sense that you don't have to know exactly what's going on inside. but it's potentially conservative because you're going to put a, you're going to put a bounding box roughly around the distribution. Gaussians don't like being put in bounding boxes. They have infinite support. Okay, but there's still some things we can do where you're even putting worst case bounds on Gaussians. Okay, so the goal for today we'll do more of a worst case analysis. And in particular, I want to show a couple important ideas for control. One of them is often called tube MPC, bless you. Okay. And then another idea is bounding the L2 gain of a system, which is related to doing H infinity control design. In both of these, we can understand them deeply and have really good tools for linear systems. Okay, H infinity really grew up around the notion of, of transfer functions and the like. Okay, but I'll try to say them in a way that connects to the time domain derivations we've already done and gives you a sense of how you would extend those ideas to nonlinear systems. That make sense? As a game plan? Again, huge topic. I always feel a little sad that we only have a couple lectures to talk about it, but I hope it gives you enough tools to look for more results if you need them. Okay, so what I want a picture of somehow propagating, boxes or something like this around this instead of entire distributions. So let me start with the linear system case. Let's consider we'll add control back in a second, but let's just think about even how the boxes evolve. Okay. Last time we said Wn was drawn from some distribution, for instance, maybe a mean zero Gaussian. Okay, today I'm going to say Wn is picked out of some bounded set. Okay. And we're going to see a natural choice is going to be polytopes. When you're thinking about distributions, Gaussians are the thing that propagate beautifully through linear systems. When you're thinking about shapes, polytopes are the natural thing to push through linear systems. Okay. And roughly speaking, the worst case analysis says, so this one tells me with some probability I'm going to get some number from my Gaussian, right? This one is ambiguous. It says it could be any W in the whole box, right? And I'm going to be conservative in the sense I'm going to say there's an adversary, and some adversary gets to pick any W in the box in order to make my controller bad, right? So I need to be robust to all of the W's in that. But let's just think about what we can possibly say about this, right? So you might say, I want robust stability, right? I want to show that a fixed point is stable, for all W's in the box. But if you remember, I made some diagrams even back in the day when we started doing Lyapunov, right, about how uncertainty can enter a system, right? And the first example I gave before was this sort of gain uncertainty. So the uncertainty was a parameter that was multiplied by the x cubed term. And that gives you a bunch of different possible systems that you might be trying to control. And you could talk about region of attraction of the fixed point. But remember, The additive uncertainty case is kind of a weirder case. The additive uncertainty is moving the curve around all over the place, right? So the notion of the fixed point is kind of broken. Asking a system that has this sort of additive worst case noise to go to a fixed point is kind of a bad question. You should instead be talking about, can I guarantee it's some invariant set? That's what we did back in the day too, was to say, can I say that all solutions are going to end up inside some region? And that's kind of the best you can hope for. Right? You can't hope for, with additive uncertainty, to just converge exponentially or something to a goal. Okay, so let's think about how to push this kind of just a basic set of results about how do you push polytopes through a linear system. Okay, and they're good to know. So first, how do we represent a polytope? So polytopes, just to get the language right, a polyhedron is something is a set that's defined by linear inequalities. A polytope is a bounded polyhedron. Okay, so this is, it's what you think of as a, something that has, the boundaries here are set by linear constraints. It's the intersection of a bunch of linear constraints. So we're going to be talking about convex things here today. Okay. There's a bunch of ways that you could represent it. So you can talk about H polytopes, which is the half-plane representation, which you typically, I'll just call it H to keep it track. We're going to have a couple coefficients lying around, a couple affine transforms lying around. So I'll say that something like this, AX less than a B, but I'll just call it H to keep it in the H polytope form. So this is just, since this is a vector, this is a matrix, this is a vector, this is a list of inequality constraints, and the intersection of them describes a polytope. It's a polyhedron in general, but if it's a closed one, then it's a polytope. You can also represent polytopes by their vertices and just say a polytope is the convex hull of a bunch of vertices. That would be like the V poly representation, or V rep. Sometimes people call them H rep, V rep. Okay. It's actually, there's a bunch of things you can know about this. The computational geometry is very interesting. Going from V rep to H rep or H rep to V rep, there are good algorithms for that, but both directions can be bad in the sense that a simply represented polytope could be extremely bad to represent in the other form, things like this. Okay. The one we're going to use more today, actually, is something that some people call AH polytope. So let me get my notation right here. So let me call the original polytope, I'll call it block P, okay? I'll say the regular polytope block P, and I'll use a shorthand H polytope defined by H and H, okay? Which is, I'm going to say that X is in Rn and Hx less than or equal to H. Okay, so I'll define a polytope P in H representation. It's defined fully by a matrix and a vector, and I mean all x's in Rn such that those inequalities hold. Okay, it's kind of a set notation. An AH polytope is an affine projection of an H polytope. And I'll write that as a set. I'll call it X. Okay? I'll call that AH. And I'll parameterize it with like this. Okay? Okay, let me write it, and then we'll think about it for a second here, okay? I mean, it's what you'd expect, okay, but take this polytope. You're allowed to move it with a little t, that's a vector, right? I'm going to shift it, and I'm going to potentially shear it or rotate it or whatever with a matrix T. Okay? So take this and allow it to go through some affine transformation. So I'll take the original polytope, and I'll just take any point in it and multiply it by that transformation. Okay, seems like a weird thing to do, but it's actually an important distinction to make, because when we're writing optimization or other things, it's actually very hard to operate directly on the parameters of the polytope. And instead, we're going to sort of call out an affine transformation of those and use these kind of coefficients as decision variables, but they operate on an existing polytope. That's what's going to go through our optimization pipeline. It actually does, importantly, so the fact that this does not have to be the same dimension, you can actually take high-dimensional polytopes, put them through an affine projection that squishes them down into a lower dimensional space, and that does all kinds of crazy things. You could have some number of vertices in the original space, and if you sort of project it down into a low-dimensional space, you can get exponentially more vertices, actually. So this is a very rich representation. Okay? But it's simply parameterized in the sense that you have some original polytope, and I'm just going to move it around. It turns out that these AH polytopes are the things that move naturally through the linear systems. Okay? How many people have heard Zonotope? Zonotope, yeah. So a zonotope is an H polyhedron. Zonotope is an H polyhedron where it's just the affine projection of the unit box. Okay. So you'll hear a lot of things in controls about zonotope math, because that's the simplest case of this, is where you just take the unit box and you shove it around, scale it, shift it. Okay, but in general, you can start with any polytope. Is that definition, that notation clear enough? Okay. So this notion of a AH polytope is closed under the operations we need, basically. Okay, so if I take, so AH are closed under affine transformations. That's not surprising at all. And Minkowski sums. That one is more interesting. Okay, so what do I mean by this? So if I have the set X, and I now have I want to write a set operation here. I'm going to multiply the entire set by another matrix A and add a vector B. Kind of a set notation, but not surprisingly, if you have something that's already an affine transform of a polytope, and I take another affine transform, it's still an AH polytope. So I can write this as AH of the other one is maybe familiar, maybe unfamiliar to you. It's the Minkowski sum. Okay, so what would it mean to take two sets, let's call them X and Y, and add them together with a set math, right? And this one I just decided it was better to grab an image from Wikipedia because I couldn't draw this well enough, okay, on the board. So the definition of the Minkowski sum is that an element in this set is such that I could take an element from the first set and an element of the second set and add them together. Okay, so if I have a blue set here, this is the origin, then elements in this, are vectors like this. Elements in Y, let's say up here, are vectors that look like this. And this red is the resulting Minkowski sum. So it's a set operation. And it just says that every element in here can be formed by taking one element of here and one element here and adding them together. And the Minkowski sort of geometry gets, you can sort of think about it for a little while, get your head around it. But for instance, the Minkowski sum of this plus this green gives you this blue. You can ignore the yellow for a second. But just this blue region. So this point here at 0.1, -1, 0. Okay, if I can basically, I can take this other thing with 0 and I can move it all the way to here. That means it's like I've convolved this thing around here, right? And I get something that goes all the way out to 1,5. It takes a little bit of thinking, but it's kind of like dragging this thing around on top of that object. Yes? It's not a convex hull because it's like going out, for instance, farther. I think of it more of a convolution. Right? You have to get the origins right in that convolution, but yes. Well, it's going to be related to that, for sure. Yeah, it's going to be related to that. Okay, so this just gives us a way to sort of stay in the family of AH polytopes. And I can write it out here. If you take any two polytopes, you want to take the Minkowski sum, you can just write a new AH polytope that looks like this. Okay. That's just the background. Here's the punchline, okay? The linear dynamics I wrote up there, AXN plus 1, AXN plus WN. Let's say I start with XN, or sorry, X0 is an element of some set X0, and WN is an element of some set W, and they're both AH polytopes, represented as AH polytopes. Then combining these two rules, I can just write the dynamics xn plus 1 is just a combination of these two. I got A times the set xn, Minkowski sum plus W. So I can take my original set. If I had no noise, then I'd just be propagating it under this rule. I'd just be constantly making affine transformations of that set as it evolved around, which makes total sense, right? I'm just taking that whole set, and every one of those is just being applied by some linear transformation, in fact, right? So that set's just going to move around. But if I'm adding in a disturbance on everything, then that actually comes in looking like the Minkowski sum. And you get these weird set operations, okay? But importantly, it stays in the class of polytopes, of AH polytopes. My chalk is getting very small. I have a bunch of small chalks. This is I need some sort of Minkowski sum on my chalks. Okay, so this gives us the stuff now of robust MPC, okay? One of the ways you could write a robust MPC. This one's, sometimes called tube MPC. All right, so now let's put some actions back in. So I have something to plan over. I'll take my same initial conditions, right? Again, so if I treat u as my decision variables, okay, so I'm going to decide I want to do MPC solve for my, I'll call them specific variables, a u with an n underneath, then I can, for any particular u, I can think about the evolution here by just propagating these sets, again with ax n plus b u n, okay, Minkowski sum with w. So given a u, it's just a different affine transformation as I shove my polytopes around. Okay, so the picture you should have in your head here is maybe I've got my linearized airplane dynamics, okay, and I've got some initial set. Say I don't know exactly where it is at the initial time set, but it's like this, okay, and depending on my control actions, I can, move it this way, that's convex. Yeah? Or I could move it over here, and I get to shape the way the polytopes evolve by choosing my control actions, right? And then the type of objective that you'd like to write is, well, that's what we have to talk about next. Like, what's the right way to specify an objective over here? Okay, but this tells me how the dynamics evolve as a function of u. Okay, and importantly, depending on what objective I pick, u enters in this thing in actually a pretty benign way. It's going to be one of the coefficients of my AH polytopes. So because it entered linearly here, it sort of stays in a nice form. I can expect to write this polytope over here is a linear function of the u's that came before it that got me there. So I'm going to be able to write convex objectives that shove around my polytopes. That's sort of clear? Yeah. No, it could be a point. And then after one set, it would be, the Minkowski set of a point with w is going to be just w after one set. Yep. I mean, you really could be, if you know exactly where you are, then just make it a point. That's fine. If you have some like state estimation uncertainty or something like this, then maybe you need to describe it as a box. Right? But you can account for even your, IMU uncertainty or whatever, odometry uncertainty as a box, and then propagate. No matter, even if I don't know where I am right now, I can still guarantee I won't hit a tree if I find a path for my polytopes through the forest without hitting trees. Okay, so a natural goal, like the kind of thing we might want to write, you can write that polytopes don't run into things. Those typically become non-convex constraints pretty quickly. But a very natural one that can be written in a convex way, you could say, for instance, that x at the final time is in some goal set. Okay, so this would be like robustly achieve a goal. Maybe I have some landing pad over here, right? And I want to say, even if the wind's blowing, even if I didn't know exactly where I am, I want my final polytope to be completely contained inside that landing pad, right? And that's the type of thing we can write. It turns out there are linear constraints that can bound, they can give you necessary and sufficient conditions for polytopic containment. Okay, that's the name for this. Okay, so that can be done completely with convex optimization. I'm going to find a series of U's, which navigates me to a subset, okay, and is completely inside that subset. That's pretty beautiful, okay. It's not, there's a chance your convex optimization solver will say no. Like, there is no U that is going to guarantee that this initial polytope can be taken through the dynamics and arrive at that goal, right? This is a conservative analysis. So it could be that your uncertainty grows too fast and it's impossible to obtain the goal set. But if one exists, this solver can find it. It's not quite as beautiful as I make it sound. If you look at the details, right? Here's the gotcha, okay? Every time I take a Minkowski sum of x with w, which happens once per time step, my description, the size of my description of the polytope, the number of faces in the polytope, grows with the dimension of my description of w. So you make linear programs, but you make big linear programs. And they grow bigger with every horizon. So you just get bigger and bigger and bigger descriptions of the polytope. They have more and more faces. Basically, the number of faces that you can have in your polytope, if we ignore the projection into lower dimensions, basically grows as the size of my description w added on every single time step. Okay, so they're big linear programs. But inside that, that's a pretty powerful tool. There's other things you want to do that I will gloss over just for time. So looking for open loop U's is very conservative. Your uncertainty would only grow, okay? You can also parameterize a feedback matrix K in a way. You have to parameterize it in a disturbance-based feedback, which we haven't talked about. But there is a way to parameterize K such that you're searching for both U and K and have a chance of getting these things to have feedback fight the growth due to uncertainty. Yes?
When you write for an optimization solver, do you parameterize the largest number of cases that you have over the whole
It grows. It's just that the number of decision variables is, n for the first one, n plus m for the second one, n plus m plus, 2m plus whatever. It just grows bigger and bigger and bigger. Yeah, it's actually worse than that because they're matrices. So n squared plus m squared plus 2m squared, something like that. Yeah. N squared plus, yeah. Okay, good. And then if you do want to put in, if you want to avoid half-plane constraints, like if you're just trying to not leave a box, then that can be a convex optimization. But if you put in a tree in the middle, right, like if you say don't go in this obstacle, that's going to be a non-convex constraint, or a mixed integer program, or something like this. Okay, but keeping the whole thing inside some convex region, that's easy. In containment, good. Being outside, bad, in terms of convexity. Okay, so roughly speaking, I think if you see pictures like, you're going to look at papers, okay? You're going to talk about, that talk about robustness, stochastic control, robust control, and you'll see airplanes or quadrotors or quadrupeds or whatever, and you'll see either propagation of polytopes, okay? Propagation of polytopes normally means linearized dynamics and worst case analysis. If you see what we talked about last time, right? If you see a similar diagram, but now you've got ellipsoids, right? Then probably these are the level sets of a Gaussian, and you're talking about stochastic, stochastic propagation. Because ellipsoids don't do Minkowski sums very well, basically, right? Like the natural thing, if you're being worst case, is a polytope, and the natural thing when you're talking about probability distributions is the level set of a Gaussian. Those are the things that propagate through. Okay, what chance do we have of doing things for, let's say, a nonlinear system? Well, we've already seen a couple examples, actually, of like, when I first introduced sums of squares, or LMIs even, the semi-definite programming, we did a robust Lyapunov analysis. And then we did sums of squares for region of attraction. We did sums of squares for along trajectories to make these funnels. Okay, so you can do, the one time if you see these pictures, okay, and you might be doing worst case analysis, would be if you're doing a sort of a sums of squares version of this. That could give you ellipsoids. So sums of squares is roughly, I'll write it out since it's been a while. These are kind of the core ideas. And you can either do nonlinear optimization, or you can do sort of sums of squares optimization to get the lift. If you want to use convex optimization and have some guarantees, you use sums of squares. If you want to have something that works faster but doesn't give guarantees, you use nonlinear optimization. But there's a path going forward for both of these core ideas up into nonlinear systems. They tend to be conservative because we don't know, only in the linear systems do we know exactly the shape of the geometry as it evolves. So instead, you have to do something like this containment on every step. You're going to say, I'm going to find the smallest region I can, which is guaranteed to be outside of this, okay, for the nonlinear system, for instance. So they tend to be more conservative when you get to nonlinear systems, but these tools do grow. In the worst case analysis, it looks like common Lyapunov functions, like we talked about before, and sums of squares funnels. SOS actually has interpretation of propagating the moments too through a polynomial system. So you can do the stochastic propagation using the same sort of sums of squares tool chains. I feel like there's somewhere in the multiverse, there's like a different branch where, I don't know, right before AlexNet solved ImageNet, someone solved like a really big problem with polynomials, right? And then Google invested in polynomials, and NVIDIA made super fast chips for polynomial optimization. And then I think I'm much happier in that branch of the universe. But I think all of these things really could go the distance, but they haven't seen the same attention. Like we're still crippled by our semi-definite programming solvers and other things, but these tools really are general purpose, kind of like a neural net, right? It would be this. I mean, in that universe, there's like the intro algebraic geometry class has 600 people, you know, from all the departments, right? And the neural network class is just kind of quiet, right? Okay, but in our universe, these are good things to understand deeply, right? And know what you can do. Let me see, where would you actually use this? So the good thing about the linear version is that this is fast enough that you could solve online. If you have a linear system or a linearized dynamic system, you can actually compute these funnels inside your MPC loop. The SOS version is more general, but it's slower. And so this has typically been used for sort of offline trajectory libraries. Right? If you know a set of motions I want to compute, and I can afford to compute it offline, then this is a good thing to know. Okay? All right, does that idea sort of work? So that's a worst case version. It's not the only worst case analysis, right? There's actually a way to do worst case with Gaussians, and it's better in many ways. Okay, but this is the simplest worst case analogy. How many people feel like they've, let's say, heard about H-infinity control? You know how to derive an H-infinity control, right? A little bit, kind of. Okay, it's good. Yeah, I mean, I think that's fair. So I found a way to derive it with riccati equations that I think is the right thing for this class, just since we've got all the background. It's not the standard derivation, but. Oh, let me make one more point. So for nonlinear systems. So the linear analysis can work for nonlinear systems. Okay? So the linear robust, let's say, can handle some nonlinearity. And so how does that work? So if I have like xn plus 1 is f of x and un, okay, and I'm going to approximate that with, well, let me say it like this. I'll say equals f of x nominal, u nominal, plus partial f, partial x, you know the drill, right? Plus partial f, partial u minus u nominal, okay? And I'll write it like this, plus higher order terms. Remember when we first did Taylor approximations, I said you could either write equality here and admit that there's some terms you're missing, or write approximately equal and not write that, okay? But there's some higher order terms here. If you basically say, I'm going to put this into W, right? If you shove your higher order terms and can bound the effect of your higher order terms, then you can push that into your uncertainty set. It can be potentially conservative, but this is an important idea. You can squish nonlinearities or reason about nonlinearities as if they're uncertainty. Okay? So people have done on nonlinear systems rigorous guarantees, and it's actually a beautiful common thing in robust control. In fact, if you want to find the best, this is not the best thing to do actually, right? You might be able to find, taking the Taylor approximation around an operating point might not be the best linear approximation. Linear plus bounded, you can optimize jointly the linear fit plus the W to get something tighter. Okay, but this captures the idea. I'm going to take the higher order terms, the nonlinear terms, and treat them as uncertainty. Okay, let me tell you about L2 gains in H infinity design. Second core idea for today's lecture. I'll do it in a few steps here. So, and I'm trying to do, like I said, I'll try to do it in a way that extends to nonlinear systems. So what we did just now, in my mind, was we took x0, my set x0, my set w, and found a way to propagate it forward in time, let's say to some future time. Let's instead do something different. I'm going to take and say, what if I take my entire Wn and write sort of the total energy of my input? You'll see where I'm going with this in a second. And can I take that as a map to the total energy of my output? There's a term for x0 too, but I'm going to ignore it to simplify a little bit. Okay, so this is one set at a time. It's going to propagate forward. It's going to give me this. I'm going to try to put an envelope over my entire signal, okay, and push that into an envelope on my entire state. So it's kind of a, think of this as like the one-step version, and this is the whole signals and systems version. And we're going to try, what we want is to actually find a bound, okay, which says that somehow, if W is small, if the total signal that I push into my system is small, then my total system response is small. Let's say I start at the origin, my quadrature is getting knocked around a little bit. If the wind is severe, I expect it to get knocked around a lot. If the wind is 0, I expect it to not get knocked around, right? And I expect that response to be proportional. For linear systems, because W enters linearly, there's a natural sort of propagation, a multiplicative effect, you know, like a scaling effect that takes it from this to this. Whereas before W had to be bounded, I can allow W to be drawn from a Gaussian. It doesn't have to be from a fixed distribution. Instead, I just need that the entire energy in the signal has to be bounded. Okay. That's like it's not that my worst case instance on one step is bounded. It's just that the total energy is bounded. It turns out to be a much more conservative, or much less conservative way to write a bound. And this thing here, we're going to call an L2 gain. These are signals, if they're finite here, these signals are in L2, okay, and this is an L2 gain. So it's just a different way to specify a robustness criteria, okay. Actually, there's a slight generalization of this. So normally we don't do it on X directly. My picture here is I've got U coming in, I've got W coming in, I've got an internal state X. And normally we'll have an output in the robust control world. We call this output Z, okay, which is our performance objective, or And it turns out, so this is just some function of x and u, for instance, that's put on the output. So I don't have to necessarily take exactly the signal in x. I can do some function of x. And we'll see in a few minutes that if I choose this to be square root of q, xn, square root of r, un, then outputting, having an L2 gain for a performance objective that looks like this is going to give me extensions of LQR into the robust control setting. So let's just generalize this slightly to say I'm going to try to find okay. All right, so how would we possibly, so we did polytopic propagation to get our previous bounds. How are we possibly going to find something like that? Like, how do we prove an inequality like that for a system? There's a great tool that will serve you well for nonlinear systems and linear systems that's going to make it happen. Okay. We're going to do something called dissipation inequalities, which are a generalization of Lyapunov functions. Basically, if I have a Lyapunov function, I can prove something converges. That's potentially at some rate if I have an exponential Lyapunov function. If I want to prove a bound like this, there's going to be a dissipation function, which if I can find it, it can guarantee something like this bound. Okay? And it's only a small generalization. So if you can find a v of x greater than 0, such that v dot of x, remember, it used to be less than or equal to 0. Now it's going to be less than or equal to some supply rate. So the picture sometimes people use to describe this is, imagine I have like a storage tank. Okay, so if my Lyapunov function is maybe some function like this, I have some noise in my system, so I have to admit that it'll somehow go up sometimes, okay? But it's never going to go up faster than the rate. So if I have a rate that somehow looks like the size of w, then I'm not allowed to go uphill faster than w is pushing me uphill. But I have to admit that if w is coming in with some non-zero signals, I might have to go uphill. Okay? And for a particular choice of a supply rate, we're going to be able to provide particular bounds. So it's just a slight generalization of a Lyapunov function, which allows you to go uphill sometimes. And the intuition is due to w. But it turns out there's particular choices of supply rates, which even if you go uphill like that, you can still make strong statements. Okay, so the one we'll use today is if I choose my supply rate to be something like this, okay? My supply is positive based on W, but as I get farther away, I expect stability to sort of fight this W, and my supply is going to go down. Right? So this is a negative. This one's positive. Okay? I'm going to choose a supply rate like this. This just says I'm loosening the Lyapunov conditions. When W is big, it's allowed to go uphill. But when I'm far from my desired X or Z, then I better be going downhill. Kind of makes sense intuitively? Well, it turns out that if you have that, then that gives you your L2 gain, right? So why is that? So if you integrate out your Lyapunov function, then you know you can get a bound like this. If I know everywhere it's less than, v dot is less than this, then the integral is going to be less than, the integral of this is going to be less than the total integral of that. Okay. We also happen to know that this thing is positive by construction. Okay. If my Lyapunov conditions were satisfied for all x, then certainly they're satisfied for x equals 0. I can just zap this. Okay, and basically this says that the integral of that has to be less than 0. Has to be greater than 0, sorry. And since this thing is exactly the continuous time form of my L2 function, this actually gives me a bound, my L2 gain bound. So let me step back from the math a little bit here, because I did that quickly. But if you can find a Lyapunov-like function, which goes uphill sometimes, downhill when you're far from the origin, let's say, then this actually, just from the Lyapunov conditions, guarantees that I have this property. It's a beautiful thing. This is the discrete time version, which is natural. You just take those integrals, turn them into sums. So the job of proving an L2 gain is almost identical to the job of finding a Lyapunov function. Okay? The Lyapunov functions for linear systems were easy. For nonlinear systems were hard. Right? LQR gave us a Lyapunov function for, from the control design. Our cost to go function was a Lyapunov function. Okay, so we can use all of the same tools with just a slightly different criteria, saying that we're going to try to have a v dot less than or equal to this. Yes. That was an omission. Yep. Thank you. Okay, so let's just throw out the definitions here, but you've heard of H infinity, you've heard of H2, maybe you've heard of H2, okay? They're all related to the sort of, well, in linear systems, they're related to the properties of the transfer function, but effectively, the H infinity norm of a linear system of the transfer function that goes from w to z is given, it's the largest singular value of the transfer function, and it's given by this gamma. So the L2 gain is the h infinity norm of the transfer function from w to z. H infinity comes from a totally different place, like typically when you present it, but just think of it as the norm, h infinity norm is gamma. And the goal of h infinity design is to find a controller that makes gamma small, ideally to minimize gamma. I feel like that was a wall of math, and I only have you guys partly with me. So ask questions, please. Yes?
So is finding L2 gain and H infinity design like the same sort of thing?
Say it again?
Is finding L2 gain and H infinity control design interchangeable terms?
So H infinity design would be finding a controller that minimizes gamma. Yeah. So it's like the control design that goes along with the verification of a particular gain. Yeah. Yes.
Is there a reason this case is limited to performance set? Are you going to use that later on in the derivation?
You can choose arbitrary performance. Well, different performance criteria will give you different controllers, of course. This is the one that this is the one that has an analogy to LQR, right? So this statement works for any z, but this one is going to be familiar when we put it through the equations. It's an interesting one. Because for instance, then you'd be able to say that my total LQR cost is going to be less than or equal to this Wn, right? So you can guarantee the cost, the performance of your LQR objective. Any other questions? Help me bring it back. Yeah. Good.
Is finding the Affine function when you slightly relax the inequality from the derivative?
Yeah, so the conditions look pretty similar, right? I think that if your dynamics is linear, then it's, and your storage function is these quadratics, then you're in the same ballpark of tools that you've had before, right? When you have polynomial dynamics, sums of squares is going to work fine for this. There's a sums of squares version of the dissipation inequality. The question, really maybe the deeper question is, do you expect to be able to find meaningful bounds, L2 gain bounds for hard nonlinear systems? This is a very natural objective for linear systems because it always enters linearly, and so you'd expect its effect to be 0 at 0 and large away from 0. And so a multiplicative bound like this is a very natural thing. For nonlinear systems, it could be that this bound, that you can't find one, right? Or that it's vacuous. But the math of finding the code for finding Lyapunov is very similar to what we've done before. Basically, almost turn the crank. The co-design is also sort of similar. It turns out, yeah, there's some hard things and there's some easy things, but the LQR one turns out to be pretty easy. Okay. I want to land this idea. I'm trying to decide based on your faces what level of detail I should try to land in. I'm going to write something that looks just like LQR, but it's actually going to do H infinity. Okay, it's just a little bit different, and it's, I think, sort of nice. You could call it, if you didn't in the vacuum, you'd call it maybe guaranteed cost LQR, but it's going to be a form of H infinity. Okay, it looks like this. I'll do it in continuous time just because you know the riccati equation in continuous time better, and it works okay. I'm sorry that I switched from discrete to continuous kind of in the middle there, but just to keep the terms flying around and clear, look different, I'll put a second B matrix subscript W in front of the W. If I have a performance objective that looks like this, I can even do infinity, but X transpose QX plus U transpose RU, and here's the trick. I'm going to throw in an extra thing that's so I'm going to penalize the system in the LQR sense. I'm penalizing it if it's away from X. I'm penalizing it if it uses big U, but I'm rewarding it for dealing with big W. There's a minus sign there. Okay? And then what I'd like to do is find my controller that's going to be the min over U of the max over W of J of X. Call it a differential game if you want. It's a minimax optimization. So the Bellman equation still works. Let me just take Q and R to be 1, just I have to write less, okay? I'm going to write just X transpose X plus U transpose U minus gamma W transpose W plus partial J X dot. In the full case, I would do partial J partial T also in the time finite horizon case. You choose J of X equal to X transpose SX. In the full case, it has the T in it. And it turns out you can take this max over T, the first one. This is now maximizing a concave quadratic in W. Okay? And it also, W comes in linearly through X dot. So I can take the gradient of this internal thing with respect to W and solve for the best play for the adversary. I can basically solve for that max W, find the best W, right? I can say the gradient of that whole thing with respect to W gives me, and setting that equal to 0, gives W star best play for the adversary. And it turns out to be simple. It gives me W star is 1 over gamma squared, BW transpose SX. I can stick W star back in here, and I get just a modified Riccati equation. And then I can solve for the min over U the way I did before. Long story short, you get a differential Riccati equation that looks almost exactly like what we had before. This is almost identical to the Riccati equation we had before. It just has this one new term. Okay. And there's a version, there's the infinite horizon version, there's the finite horizon version. But the punchline, you see, is that I can solve this riccati equation just like I did solve for LQR, okay? We always had to check if the riccati solution had a positive definite solution. So what happens if you cannot obtain, you might choose a gamma that is, if the gamma is too small, then it's possible you cannot find a positive definite riccati equation. So basically, same with LQR, when you call it, it says, here's the optimal K and S, or it says, sorry, your system's not stabilizable. This one, if you call it with the gamma that's too, that it cannot achieve an L2 gain of this small, it'll say, sorry, there's no L2 gain. I can't find a controller that will achieve that L2 gain. Okay, so it's sort of a similar thing. Right? But if you can find a solution to a positive definite solution to this riccati equation, then you found a controller which is almost identical to what you had before with just a slightly different storage function. And it's the optimizing, it's the H infinity design when Z is the LQR objective. Okay? And the great thing is, you remember I always wrote J dot of X is less than or equal to L of X U, right? That was always the analogy we made between cost to go functions and Lyapunov functions. Well, now this one, the J dot of X, is less than or equal to my X transpose QX plus U transpose RU minus gamma squared W transpose W, right? So it's exactly a dissipation inequality that proves the L2 gain. Okay, so in practice, what you do, unfortunately, you can't jointly search for gamma and U, but for every gamma, you can solve this, and at some point, it will say, no, I don't have a positive definite solution. So you basically just do a line search. You try to bring gamma lower and lower and lower, keep solving riccati equations until you find the smallest gamma that will achieve this. And that is your minimal L2 gain, which is your H infinity norm for the system. All right, so stepping back for a minute, right? There's we did two different things here. The first thing, pushing polytopes through, that was a bounded disturbance, and it was a reachability argument. You basically said the reachability is in sense of the adversary, right? So the worst case adversary, these are the set of states that he could possibly drive me to. Okay. This one is now an input-output gain, saying that if the magnitude of my disturbance, of my adversary, is bounded, okay, then the magnitude of my response is bounded. They're different types of analysis, but they're both connected. They're both absolute inequalities, bounding the total performance. One is relative, and the other one is absolute. Yes? Yes. Yep. Like in both cases, we're going to take a worst case over W. The adversary is allowed to pick the worst possible W, the most disadvantageous W. And basically, the long and short of this is that the LQR derivation you already know can give you an H infinity design, a particular form of H infinity design. It's not that different, but it does give you different control gains. If you say, I need a controller, this is the way that my disturbances come in, and I need my L2 gain to be less than this amount. It will give you a different set of gains out. Yeah? Yep. I mean, I think this is a pretty lightweight. In terms of the line search solving riccati equations, it's pretty lightweight. it's less general than the LMI approaches, right? So it's the same thing I mean, a lot of our LQR kind of things, you can solve LQR, the deterministic LQR with an LMI too. It's cheaper to solve the Riccati equation. But if you want to do LQR design subject to some other constraints or something like this, then you use the more general form.
So if you use that as like this, it would be, I guess, how much reason does it
I think that's right. Yeah. Yeah. Okay, and then this thing also, the generalization to nonlinear systems, the analogy I want you to have is this dissipation inequalities. That was used in a narrow sense for the H infinity result, but in the general sense, that's as general as the Lyapunov functions. You can make these kind of bounded arguments for nonlinear systems. Again, sums of squares, neural network Lyapunov functions, they all have different strengths. All right, so push probabilities through and track probabilities and write objectives on your probability distribution. Push sets through, right? Or do a relative error, saying the magnitude of my response needs to be some relative magnitude compared to the inputs that come in. Those are kind of the three variants that we've been talking about. Right? They're all useful. They're all a stone's throw away from the things you've been doing problem sets on. Okay. Good? I'll stop there. Yeah.